March was a month.
Yeah, it's coming up fast.
So, I forgot I had to plug this into the projector. So what questions do y'all have while I'm plugging this up? Any questions about the lab?
For the search, do you just want to search for one element?
Yes, yeah. So you search for an ID, and it'll return the student back to it.
Okay, but which, doesn't matter which one we search for.
What do you mean?
And like the test.
Just a random element, right?
Yeah.
For JUnit, you just move the jar file into the library.
Well, I made JUnit tests in the project themselves.
Right, my version of Eclipse, I never put
Oh,
JUnit in.
I don't know how I forget how you set it up the first time.
I forgot to.
Yeah,
I just renamed the file we downloaded and started adding new classes.
it's probably not a bad way to do it. That's what I would recommend doing. Yeah. Yeah, I can't remember. The internet can help you with that though. But yeah,
Author is Aaron,
you were feeling lazy.
I would feel bad if
Well, and you
I
need
went
to.
into interfaces that are Word.
Yeah, well, you're allowed to. I mean, I gave it to you to plagiarize it. It's it's always funny to me when when I'll have particularly intro students they'll go to Stack Overflow to find help on something. Eventually, they'll find out about Stack Overflow because some upper level students introduce it to them. It's and Stack Overflow is fascinating because you get stuff that's usually like not a bad starting place, but then people will go like if like this is the correct path that one should go on, Stack Overflow will often get you there, and then goes like whee, and gets on this one, and someone's like, "This really solved my problem. 5 million upvotes," and you're like, "That is crazy and insane." Like you've taken something that should be 2 lines of code and made it 5,000. That's bad. Just because of 500 other self-taught high schoolers think this is a really good way of doing it doesn't mean it's the best policy. But it is a really good way to find method calls. But anyway, so I'll get people intro students who will use Stack Overflow and copy and paste Stack Overflow code into their thing to solve a problem. But what's really funny is when it's stuff that I've directly given code in class, and they'll not want to use the code that I gave them, but would want to use Stack Overflow because they didn't want to just copy what I did. And I'm like, I gave it to you to copy.
It's open source.
It's open source. When the professor gives you an example, feel free to use it. And they're like, but I felt like it was cheating. And I'm like,
Well, you cheat
it's called learning. But I'm like, I appreciate that you want to do it on your own, but taking someone else's bad code and putting that in there doesn't solve.
And then like that way you don't know what it's going on. So you can't comment it.
Right? Yeah, you can't comment it, and
Yeah, and all the Stack Overflow stuff is just confusing as hell.
Yeah. The way that I use Stack Overflow is when I have a question about something, like for example, I forgot nanosecond was the timer. So I'll search Google, and that almost always takes me to Stack Overflow for how do you measure timing in Java. And that takes you to the Stack Overflow page as the first result. And the Stack Overflow page is crazy and insane. But they'll typically mention an API in there, which is almost always something which no longer works in current Java or the current version. But then you search for that, and then you get the web page which says, are you using this in your code? You should replace it with, and then it gives you the correct one. So it's usually a good place because it gives you the wrong version, which you can then search the internet for, and that will tell you the correct version to do. But yeah, Stack Overflow it's a good idea. It's better than Wikipedia, but that's a low bar. But yeah, Wikipedia is great if you want things to be if you want to know about anime or video games.
Yeah, so, video games, like, if people put wrong stuff in there, they police that thoroughly.
Yeah, it's like that is on the ball. It's not called Secret of Mama, it's called Secret of Mana. So anyways.
See when they put in Mama games, they can see the
Anyways, so let's talk about, and I'm glad we're recording all of this conversation. And I'm not getting your responses to it, so it's just me talking like a crazy man. And we're posting on YouTube, so it does seem like a crazy man talking. We need to mic the audience.
It's gonna become viral.
Yeah.
Crazy professor.
Crazy professor talks itself. We need to mic the audience for these classes. Fortunately, I'm in disguise wearing glasses today, so no one will know who I really am. I like that. Also, one last divergence. I like the thing where they're like, no one knows who's Superman and Clark Kent are the same person because Clark Kent kind of stoops a little bit. It's like really, no one can fucking figure out like this is Clark Kent and this is Superman. It's like, wow, Metropolis people are stupid. It took Batman to figure it out. Anyways, so let's talk. So we talked about delete last time, which I want to remind you, you don't have to do for 2-3 trees. I really want to stress this because delete on 2-3 trees sucks. It is a very, very difficult thing to do, and I don't want to have to put you guys through that. But everything. So delete, aside from fixed underflow, takes constant time. And if you look back at the delete algorithm, it makes sense because there's really nothing going on here aside from you have to search for the node, so that takes log n time. But the real heart of the delete algorithm itself is log n, is order 1 time. Nothing really going on in there aside from fixed underflow. With fixed underflow, you have a constant number of operations for each level. The difference with fixed underflow is that because you can do this, you have to recursively call fixed underflow, you have to go up in each level of the tree. And so the number of times you can call fixed underflow is equal to the height of the tree. Because you might have to fix something at this level and go up and fix something there. In the worst case, you're actually going all the way up to the top. And if you're going all the way up to the top with fixed underflow, you also know that you're decreasing the height of level. That's not relevant for time analysis, it's just a fun fact. So we proved the other day that the height of a tree is equal to order of log n. So the fixed underflow algorithm itself takes order log n time. Again, that's not a formal proof of this because fixed underflow uses as a recursive algorithm, and I haven't given you the tools and techniques you need to be able to prove time complexity with recursive algorithms. You just have to make sort of the casual observation that at each level we're doing a constant number of operations, and we have log n levels where it could operate. So that means it's going to be a log n time complexity. Does that make sense to everyone? Sort of going back to 2-3 trees, we can look at the time complexity of these, and what's the time complexity of insert? Log n time. What's the time complexity of extract max? Log n.
It's supposed to go all the way down.
It probably goes all the way down to the far right, extracts that node, and then
Even though you know it's going to be on the far right, it's
right.
You don't know how long.
You also have to go down log n levels to find it. How about get max? It's log n as well because you have to search all the way down to the bottom right. How about is empty? Constant. So all you have to do is check to see does the root exist. How could I make a small tweak to get max? Get max, insert, and extract max. That would add constant time complexity to insert, extract max, and would make get max run in constant time.
Here's a variable.
To see how many.
Yeah, so what you do is every time as part of the insert and extract max, you also, whenever you insert, you keep track, are you actually are you adding something which is bigger? If you are, you sort of update a max value for the whole thing. extract max whenever you remove it. You also do then a search and find out what is the second biggest element. So you sort of preload the system with, okay, I know this is going to be the max, and I'll get it later. Now, here's the trick about this. Have I saved any, like, if I do the same number of extracts and get maxes, does it make sense? So let's talk about the mix of extract and get max. So suppose I have, let's say, 1/3 of the time I insert, 1/3 of the time I extract, 1/3 of the time I get max. Will it save me any time if I'm always keeping track of the max variable as sort of an additional thing? So I have my 2-3 tree here that keeps track of the main structure, but I also have an additional variable which is location of max, and that always points to the farthest right thing in there. So I'll have to update my insert and search to update the location pointer. So if I insert something that's bigger, I have to update the location of the max. If I extract max, I have to update the location to figure out where the next one is.
Get max still take constant time because usually they return the value,
Right.
but yeah, this will still take the same time because extract max will still have to
So-
go dynamically.
Here's the thing: is they actually take the same big O time. They both take big O of log n. The running time of these though will slightly increase. Insert minorly so. Insert is a really minor addition because all you have to do is check: am I inserting a value that's bigger than the current max? If I am, just keep track of where I inserted it and then update that. So it's really one additional compare and then one additional store. That's a very, very small increase in the amount of work that you would have to do. Extract max, on the other hand, has a little bit more work to do because it's going to have to do some navigating in the tree. It's going to have to remove the max from the tree and sort of keep track of what is the next smallest one as you're doing it. And that could potentially be a fair amount of work. It's not necessarily going to be because you're already sort of living in the bottom right-hand node. So it's not going to be terribly more work, but it will increase the amount of work that you do for extract max. However, it does have this benefit of making get max really, really, really cheap. So when you talk about implementing these things, this is not such a bad implementation deal for a couple reasons. One is the increase, because when you do an extract max, is less than doing the full get max search every time, because that's a full log n levels. Extract max, if you're really clever about it, you can make sure that it's just a small amount of increase that you're going to be doing because you already found the bottom rightmost node. Insert, as we talked about, is a very small increase as well. So sort of cumulatively it pays off. The other more important thing about this though is that most of the time with priority queues, you're not having this 1/3, 1/3, 1/3 mix. You're actually getting the max more often than you are extracting or inserting. In fact, getting the highest priority element and reading from priority queues is more often the case than not. And so there was a question a while ago, I think it was Rob, was it Rob or Gabe? Someone over here, who asked about mixing data structures. And there is a very common case that happens where you'll have a backend, like a 2-3 tree, which works in log n time, but has a lot of overhead associated with it. And so that sort of is your master data backend for everything. But the things that you know you're going to be accessing, so like not just the top element, but the top 100 elements, you might keep in a linked list, which is much faster access. And so you're not just extracting one element, you're actually extracting to the top 100. And you keep that in a separate data structure than the other 5,000. And that's something which can happen, and when you really need to care about performance, that's a trick that people often use. It gets really tricky though, because you've dramatically increased your likelihood of failure, of losing data, but when you're moving between the two data structures. So that's the type of thing that you want to implement way after the fact. When you're like, okay, performance is really taking a serious hit here. Let's figure out how we can solve this really serious performance problem. Any questions about that? So we talked about that. So the next steps, as we talked about, these are a specialization of B trees. B trees have an unbounded number of nodes, of values in each node, and that value is determined by the physical characteristics of the hard drive itself. We talk about this a lot in databases. So if you end up taking databases, the B trees sort of are where you live. They are what you will use. There are dozens of types of balanced binary trees. 2-3 trees are one of them. There's mergeable. There's mergeable stacks, balanced trees, where it's very easy to take two priority queues that are already perfectly balanced and have a good time, and then the merge operation, which merges the two lists together. That turns out to be really useful when you talk about scheduling, because you can make lists of things that are due at a certain point in time and then merge them back together. There's red-black trees, which are sort of really people's go-to balanced binary trees. We don't talk about them in here because they're a little more complicated to set up and program than 2-3 trees. We talk about them in data structures and algorithms. There's also AVLs, which are another approach to balanced binary trees. And every one of these balanced binary trees has specific scenarios where it's useful. This is part of the reason why I really highly recommend people take algorithms if they have a chance to, because it's good to go through sort of a couple of these, and more importantly, it's good to have the ability to be able to read these algorithms and figure out which one you want on your own. And that is often the case when you are choosing these more algorithmic problems. So when you get into industry, what ends up happening is most of your work is it's the type of stuff that you would do in 120 software engineering. It's a lot of mechanical work, making sure these APIs work up, making sure this interface glues up, making sure these things are much more mechanical. There's not as much of these big picture problems that you tend to get in this class. That being said, these big picture problems come up and consume weeks and weeks and weeks of time because they are the heart of the algorithm. And they also are fun because you and a couple of your friends go to the whiteboard and figure out what's going on. But every scenario is entirely different. And so it's really good to have this backlog of all these different approaches that you have. So like a master chef, you know what's going to happen when you mix the right levels of sugar and yeast. Has anyone here tried baking bread before? So what happens when you mess with the ratios? Yeah, it goes to shit fast. If you try and bake bread, they are really, really precise about put 1.5 tablespoons of yeast, 3 tablespoons of sugar. If you mess up on these ratios at all, the thing will not work. It'll come out literally a disgusting pile by being off a half teaspoon less on sugar. And it's really weird because you mess up a little bit and everything goes to hell. You're like, what? But when you, with computer science and algorithm analysis, you have to have this cookbook and you have to know how these things fit in there. And so having that in your backlog is a really important characteristic. So that's it for trees. So I want to move now on to graphs. Any questions about trees before we go on? So I want to talk about graphs, and for those who have had Core 2, you've already you've worked with graphs a bit so far. Graphs are heavily used when we start talking about networks, because if we look at how computers are set up, we have a router. That router is connected to multiple computers. It may be connected to other routers, which are then connected to other computers. Those might be connected to hubs and all sorts of other devices which are interconnected. We model this via graphs by having one data point for each one of these, and then we have an interconnectedness between them. And the formal definition of a graph is a pair of what are called vertices and edges. Now, it's important to note that when we look at graphs, trees are a special case of graphs, because trees, graphs are any connection of data nodes or vertices, and then edges that connect them together. So we have vertices that are connected like so, and then we'll put one back there. So we have three vertices, A, B, and C, and they're all connected to each other. This is a graph. You're in node A, you can go to B. You're in node B, you can go to C. Or from C, you can go to B, or you can go to A. This is actually a fully connected graph because every node is connected to every other node. This is another graph. You're in node A, you can go to B, you can go to C. This graph reminds you of anything?
Already came up with
It's a linked list. How about this one? I would, it's the difference between this and a hash table is a hash table has a random entry point into these, and these do not. That's a good guess, though. Anything else?
tree.
A tree. A alpha. It's another tree. This one's probably a 2-3 tree.
Wouldn't C have that?
It depends. It depends. No, C does not. Doesn't have to. No, C would not have to have an. Let's try and draw this up for. So A, alpha. Yeah. So it's not so much. These. That's the problem with actually these not having nodes. There we go. We tend to draw trees like this because it makes our life a lot easier. But we can draw them any way we want to when we start thinking about graphs. If you decide to draw a tree like this on your test, I will shoot you. Technically, it's correct, but in this case, that's the worst type of correct. Don't draw trees like this. You'll drive yourself mad. You'll actually more likely make a mistake on it. Trees are typically drawn like this, but this is a graph itself. All trees are graphs, but trees have the property that you always have a parent node. You always have siblings. Everything always goes back up to one root node, and there's no cycles in here. And that's a really, 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 really important concept. There does not exist a connection from this node back to its parent. That is extremely important. What? Graph. So, yes, yeah. This is now a graph and no longer a tree.
Oh, okay.
Yeah, we've now made it solely a graph and no longer a tree by adding an edge from the bottom up to the top. There are different types of edges. There's directed edges, and those only allow you to move from one to the other. So if there's a flight between Orlando and Florida, thank you. Orlando, going from the beautiful city of Orlando to the beautiful state of Florida. So if there's a flight from Orlando to Dallas, apparently I don't know where we live. That's a good case for a directed edge because you are talking about movement from one location to another, and you can edges, and this was not something we talked about here because our edges had no value typically on trees, but on graphs, edges themselves are allowed to have values associated with them. And so the value associated with this is the flight number that moves from Orlando to Dallas. An undirected edge is just talking about the connection between the two. So a good case for that is I want to talk about the distance between Orlando and Dallas. That's talking about the miles between the two. A directed graph, all the edges are directed. An undirected graph, all the edges are undirected.
Is there any reason?
Wait.
Is there any reason they call the first one U?
What?
For directed edges. This is the first vertex. U is.
It's just this. It's just U and V. It's just U. The difference is that when you talk about a directed edge, it's always the first value to the second value, and so there's actually you carry the order of those. With an undirected, you're always talking about U to V implies that V to U is also in there. So it implies that both of the edges are in there and have the same value if they have any. So it's really an undirected edge is really, it's the way when we write this up using set theory is not just one single pair of vertices. We actually write it up as though we write it up as two directed edges that both have the same value. So there's U to V and V to U, and they both have 849 on them. And so an undirected edge is also a bidirectional edge.
Can you have a graph of both?
Yes. It doesn't happen as often. You can have them with both. Typically what will happen in that case is it's more that there's direct connections between there. And so if I were talking about this, yes, there's flights between Orlando and Dallas and flights between Dallas and Orlando, but the flight numbers are going to be different between the two. And so you'd have directional edges, but they wouldn't have the same value. So you'd have directional edges in both ways, but they have different values associated with them. Here, there's a, it doesn't matter if you go from Orlando to Dallas or Dallas to Orlando, it's 849 miles, either way. The distance between the two is the same. And so that's why you typically, when you have undirected edges, everything in there is undirected because the information you're conveying doesn't matter where you're coming from, it's just that the connection between them. You can use graphs to talk about physical connections between objects. And so we talk about mutual exclusion graphs, where we talk about readers and writers. So if there's an edge between two nodes in here, then they can't access a file at the same time. So writers can't access the same time as other writers. Writers can't access the same time as readers, but readers can access together. And so you can use graphs to represent interesting characteristics like that. You can also use graphs, and let's pull up. Let's go to the handy dandy internet quickly.
So readers can all go at once because they're not connected.
Right. Yeah. No. Let's talk about Pac-Man. Do y'all do Pac-Man in 120?
Yes.
Define
If you haven't played Pac-Man, it's
So let's talk about it a bit more. And you're like, oh god, get some more donuts. The thing about Pac-Man, and the reason why I bring it up, is that Pac-Man can actually be represented using a graph. And so what you do is, unfortunately this map doesn't have pellets on it, but every time there's a junction, that represents a node. And so the graph for representing this would be, you have a line there, 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 and so on. So you can actually make a graph representation of how the nodes are interconnected. On top of that, the values associated with these would be the distance or number of pellets between them. And so if there were 10 pellets there, that would be a 10 pellet distance. That might be a 2, 1, 1, 2, 1, 2, and so on. You can also classify nodes as either being sort of a normal, or it can be a super, or what are the big ones called? Giant, big, where it actually contains the information. So now what you have is once you've put your data in here, you're not navigating a maze, you're moving Pac-Man and the ghost around the graph. And it becomes a lot easier to talk about it because it's now about the rate at which they move across there. Where are they in the graph? Where are they in the line if they're moving slowly across? And this is the way we typically, whenever we have a maze, we want to represent it using a graph because it makes navigating it so much easier. Is this how you all did it in 120 or?
Did it with the graph,
When we did rays or lister, two rays, most of us.
I did too.
Oh, so you had an entry in the array for every square. And that's another way to do it. The difference between that approach and this one is that if you have a 2D array, you end up having an entry everywhere, right? Now, you end up having a whole bunch of entries that are dead. With the graph approach, even if you were to have a node for every entry, which is also another way you could do this if you want to make it a really dense node as opposed to putting distances on here, you make it so that you have just a node for every space and a connection of 1 in between them, which is another perfectly legitimate way to do this. The advantage of doing the graph approach, though, is that you have nothing in those whole spaces. So you don't have to keep track of those. Additionally, it makes it easier when you get to corners to tell which way you can turn, because you know if you have an up, down, left, or right connection from there. I assume what you had to do is actually physically look up in the array, down, left, or right, and see if there's an entry in here. This makes it easier because you can do null checks and be like, is up null, is left null, is right null, so you can make navigating a lot easier. Using a grid representation like that, you did make a graph. You just did sort of the cheat implementation of a graph. The better implementation, do you have an idea of what the better implementation of it would be? To make a graph node that say had, I were to tell you make a Pac-Man node, what would be the number of variables in here?
Distance.
Not quite.
Like a blue.
So let's talk about first what data would we like to keep in our individual node.
Is there a pill or not?
Yeah, so there's a super pill. I think that's actually what they're called. Super pill.
Maybe.
Yeah. So we'll have a Boolean super pill. What else will we need?
This regular.
What?
This is a regular.
There's a
Regular pill.
regular pill. Bool, regular pill.
And if there's a ghost,
Do we want a bool for that?
I think.
No, because there's different ones.
Right. And you can actually have multiple ghosts in the same square. They can collide with each other. Yeah, and
They can pass over each
they can pass over each other.
They're ghosts.
Yeah. So what type of data structure do we want there? You know, multiple ghosts in one square.
Or just
Arrayless.
like three. There's 3 ghosts.
What's another way we could do it that would be special for Pac-Man? Do we have an unknown number of ghosts?
No.
No. So we could cheat with Pac-Man because we know we have Blinky,
Pinky.
Pinky, Something Clyde.
I did it perfectly.
Yes.
What is it?
When Inky did it, I
Kinky?
did.
Inky. It was like, Kinky doesn't sound right. Yeah.
I had the ball.
Yeah, Blinky, Pinky, Inky, and Clyde. So you could actually make Booleans for those four.
Yeah, Clyde.
You could make Booleans for those four if you felt so inclined. Wouldn't recommend doing that. I think an array list is a better way to do it, but it might be faster to have the 4 ones because you know you're only going to have 4. So what else would you need? Pac-Man? We only have one Pac-Man on here, so Google Pac-Man. Let's assume no fruit. That's annoying. You guys are like, we already checked out on that one. So this gives us sort of the player information for what's supposed to be in there. So what do you do now? That what other information would you need to have in here? You need to have, so we'll call them node up, node down, node left, node right.
Put them in an array.
So is that like,
Wait, sorry.
is that like
No, this is not so much collision detection. This is so that way, if I'm in this node, I know who my right neighbor. I know the node that contains my right neighbor. So you remember in the graph, like when you were drawing a tree. So have you started the binary tree one yet? If you haven't, it's so you have every node has a left child and a right child, right? And they're both nodes in and of itself. This is the same thing, left and right, but because it's a graph, there's no root to the whole thing. There's no parent for the whole spot. It's just graph. So you can't just keep track of your left and your right and your parent. You have to keep track of everyone around you. And in a Pac-Man grid, you have 4 neighbors. Up, down, left, right.
Can you not put them in an array?
What?
Can you not put them in an array?
You could do an array list. The difference with the array list, though, is you end up having all of these empty spots where nothing is going on. Now, for a Pac-Man grid, you're not wasting a lot of space here. But when you start talking about more complicated mazes, you end up wasting a lot more space with these areas where nothing is navigated. So an array list is a legitimate implementation of it, but you tend to waste more space doing it. This also makes it easier to navigate because now you can do is up null. If up is null, then you can't go that way. Is down null? Down's not. And so it makes the navigation of it easier. Now again, you can fake this with an array list, but when you're doing an array list, you're actually creating an implementation of a graph on the back end without actually knowing that. The mathematical structure that represents this is a graph. The array list is an implementation of it. That works, but it's not the most elegant implementation of it. Does that make sense? So yeah, you navigate the whole thing under this approach. So that's one application of graphs. Graphs really occur whenever there's junctures between multiple points, and graphs are really shockingly useful. It's surprising how often they come up again and again and again. In fact, as Higgs will talk about in AI, a lot of artificial intelligence is how you navigate graphs. And that's a big part of AI is how do you navigate graphs and trees intelligently. So with that in mind, let's go back and do some more, let's talk about some more terminology. So endpoints of a graph, we have n vertices for a particular edge. So every edge is connected to exactly 2 nodes. The endpoints are the 2 edges that are on the ends of that. The edges that are incident on a vertex are the vertices that are touching, are the edges that are touching a particular vertex. So on U, the edges that are incident on U are A and C. Adjacent vertices are adjacent if there's an edge connecting between the two of them. The degree of an edge is the number of connections that edge degree of a vertex is the number of connections that vertex has. Two edges are parallel if they go between the same two nodes, but have different values associated with them. Self loops are edges that loop back onto that where the vertex is both the same. Self loops occur a lot. Any questions about
What did you say degree was?
degree is the number of edges that you have.
So every U is only 2.
Yeah, for U it's 2, for V it's 3, for X it's 1, 2, 3, 4, 5, for Z it's 3, for Y it's 2.
What is the occur J? And why does it have a link to itself?
This is a self. This one.
Yes.
That's a self loop.
Why does it do
So sometimes you want to be able to loop on yourself. One thing we'll talk about later is in theory of computation is string parsing. And what's going to happen when you talk about string parsing is you're going to have a graph that represents all of the possible letters you can accept. And so what ends up happening is you might keep on looping back on yourself again and again and again and again. So suppose I want to write a graph that represents strings that, let's talk about writing a graph that represents numbers. And so when I get to a special node that I'll call the accept state, then it means that I'm done accepting strings. I'm done accepting characters. So I would self loop here 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and then this one I'll label space. So what I would do here, if I were to see the string 321 space 562 space 785, what I would do is say, okay, 3, I have a self loop here on 3, go back there. Oh, 2, self loop on there for 2. Oh, 1, go back there on 1. Oh, space, except that's an integer. So it keeps you in the same state over and over and over again. There are some types of graphs that force you to be moving to a new state with every turn. The only way to get you to stay in the same state then is to allow for a self loop. In fact, you can view Pac-Man like that, because under Pac-Man, you can't stop moving unless you hit a wall, right? People are like, oh, I blocked out Pac-Man from my mind. No, it's actually the self loop back to itself. So that's why you would have self loops, is that you have to make a move with every time. It's a great question because they're not always useful, and sometimes they don't make sense. For example, if we're talking about flights between cities, am I going to have an Orlando to Orlando flight? I mean, yeah. I don't know why you would do that. Yeah.
Canceled flights.
Yeah, canceled flights, but you just went to Disney World. Where are you gonna go? Disney World again. You would have the whole experience. You just did Disney World, and now you want to do Universal Studios, and you don't want to have your one trip sullied by the other. So you take off and then land back in Orlando again. But no, the reason we don't have self loops in all graphs, but they are there in some of them, and they need to be allowed. So it's for graphs where you have to make a move each turn, or for graphs where there's a cost associated with it. So it might be that it's better if there's graphs can also denote the cost of doing something. And so it might be cheaper for you to move on to the next step than to actually stay where you are. So if you're on the run and you're trying to create a graph to represent how likely are you to be caught by the cops, you have to make a move each turn, and every turn it's more likely if you stay in a city you'll be caught by cops. And so you need to move on to the next one. I'm sure all criminals think with algorithmic graph theory. It seems logical to me.
Snowden probably does.
Snowden probably does. his graph is nothing but self loops though.
Stay in Russia.
Yeah, Russia.
Move to Russia. Stay in Russia.
It's actually known as Russian airport.
Oh, yeah. Good as Tom Hanks.
Yeah, yeah, that's his graph. Rest of world. Russian airport. So yes, so Snowden's a good example. He has to make a move each turn, and that turn is stay in Russia's airspace. I guess he's actually left the airport now. Russia's given him an amnesty to move around the country, in the unbelievably free country that is Russia. Yeah. At least you got to go to the Olympics.
Oh, we're doing it.
Probably. I mean, just chill there. I don't know if he cares. Yeah. Chill. Apparently, it was like blisteringly hot. It was like warmer there than here.
Apparently,
When
snow.
What?
Apparently, it's like not good when there's snow.
Yeah, the snow was all fake.
Yeah.
Like they brought in snow. It was like 60 degrees during the award ceremonies. Yeah, it was like apparently the whole thing was fake. They had been stockpiling snow for years to like. I'm not making this up. To ship it in.
That was their plan. Once they take
But-
over a country, they import snow.
I have to say that like these James Bond villains are getting really, really sad. Like we will own the world's snow supply. Okay.
It is confiscating ice from the world.
Yeah. So let's get through a few more terms. Paths. Paths are the way in which we navigate through here. So we start off, and this looks a lot prettier when you see this slide down below. Path. So we can talk about a path would be go from U to W, from X to Y, back to W to V. And so it's the way in which we navigate it to move from between 2 points. A simple path, every vertex is distinct. So V to X to Z. That's a simple path because no node repeats. A non-simple path would be this red one because we actually repeated W twice. Last one, and then we'll quit for the day. Cycles. The first is a path where the first and last node are the same. A simple cycle, the only path that repeats is they only have one node that repeats, and that's the first and last. A non-simple cycle, same thing as a non-simple path. You have multiple nodes that are repeating. Except now the first and last node are also the same. Cool. Well, that's it for today. Where's my mouse cursor?